Hi everyone, and welcome to the third lecture in this mini course about particle physics, a crash course for mathematicians. Please, Veronica, go ahead.
Thank you, Daniel. So good morning or good evening, everyone, and thank you for attending this third lecture. So before starting, let me first recap where we are in the path of what I planned to discuss in this lecture series. So we talked about the main issues some of the main issues that string theory and particle physics as a whole is trying to address. I'm trying to express this in the language of category theory. Up to now, we've done that, looking at how symmetry topological field theories are useful as complementary perspectives of quantum field theories to describe the spectrum of operators and charges that can result in a specific theory, and how you can change the spectrum of the theory by changing the topological theory that lives at the boundary of the symmetry TFT. So we also have seen specific examples in the case of sigma models and gauge theories and nonlinear sigma models where we combine the two, and how partition functions can be turned from relative to absolute by selecting a specific subgroup of the gauge group of symmetries that act on the theory, and by gauging away that particular subgroup. So gauging, we've seen that gauging a particular subgroup corresponds to selecting a particular subcategory of the category that lives in the bulk symmetry TFT, and mapping that, projecting that to the identity of the new symmetry TFT that results once you've gauged away that particular subgroup that you've chosen. So corresponding to this procedure, you end up having a theory that has a different spectrum of operators living in it, which means a different set of electric, magnetic, and ionic charges. So for the time being, in the explanations and examples I've shown you in the first two lectures, especially the second one, I have not touched at all the content of supersymmetry, which is at the heart of this top-down approach that I'm trying to explain. This lecture is instead going to turn into a more direct approach towards the supersymmetric theories that we want to analyze, because we know that we need supersymmetry for string theory to be the most likely candidate for unifying theory as a unifying theory of fundamental interactions. Of course, we know supersymmetry needs to be broken to describe the real world. In fact, I'm not going to show you how to get to zero supersymmetry from this top-down approach, because there's still no mathematical machinery that enables us to do so. But still, there's a good control of how to deal with it by performing partial supersymmetry breaking in suitable setups where we know that maths is still able to, with the formalism that we are provided, is still able to give us an exact description of the theory that we obtain. So my motivation to show you these supersymmetric setups is not the direct contact with the real world that we have, but it's to show you that there is a formalism that needs still to be completed, but it's a possible, very promising direction to pursue. So last time, the last things we discussed were Hochschild cohomologies in the context of factorization homologies in two-dimensional topological orders. I told you that there's a correspondence in between symmetry TFTs and topological orders, and the importance of that is that you can map higher dimensional symmetry TFTs, which are much more complicated to even visualize because of the high dimensionality of the problem, to two-dimensional topological orders, which instead we can have a much better grasp even intuitively. Obviously, there's a price to pay for that dimensional reduction, which is a much more intricate algebraic structure that results from the need to keep track of all the Bradens and ribbon structures that are needed to be for the category of the symmetry TFT to be faithfully described in this two-dimensional setup. So I showed you last time that factorization homology is very different according to whether you can have contractible or non-contractible loops. And this is a property that shows you how the two resulting theories that are separated by the loop that you're trying to shrink are actually related by some kind of duality. So dualities, I told you, are very important in the perspective of physics, especially because they enable you to map different theories among each other. So for the case of string theory, we know that different string theories are related by S and T duality, for example, but there are also other dualities in physics, such as three-dimensional mirror symmetry or homological mirror symmetry. And all these symmetries are important because they let you describe some features in one theory in a way that are much easier to deal with respect to another. And then you can just use the duality that you know to exist to map the results in the other theory, which would be much harder to calculate instead. So this is the reason why it's important to use these tools in the context of dualities, which we will see will arise in particular examples. So before going into supersymmetry, I would just like to finish some things about the two-dimensional setup that I started off describing last time with the topological orders, just for you to give to keep in mind for when we're going to next. So the last thing I mentioned last time was the non-contractible loops, where we saw that you can't define point objects in the sense that if you try to contract a loop, the loop is going to give you a point which encodes a non-trivial algebraic structure in it. So this allows us to split topological quantum field theories into two main sets that are they're described as functors in this slide that you see. So they are called either fully extended or non-fully extended. So the difference in between them is that they're both two functors. So I write here the two functor, which is the topological quantum field theory. I call it Z just because this reminds me that this, if I'm able to define this fully faithful functor as a functor in between these two categories, then I basically have the partition function that describes the theory in question. So I can access all the field content and interactions, etc. So I know everything about the theory, and I can calculate the correlation functions, for example. So the fully extended one is the one where the source category, which I call here Bordism, this stands for Bordism, we'll see why, but stands for Bordism. The numbers 2, 1, and 0 stand for respectively the objects that are two-dimensional cells, because we are in a two-dimensional topological quantum field theory. 1 cells, that will be the loops that separate topological orders, different topological orders, and 0 cells that are points. So in this case, I can define all of them because I can contract loops. And loops can, once you've contracted loops, you obtain points. And those points carry something that is just something proportional to the identity. And if I can define this in this way, if I can define all these three elements, which would be in the categorical perspective, they would be objects, 1 morphisms, and 2 morphisms, then the theory is said to be fully extended, which means fully extended to the point. This is why this is the term that's being used. On the other hand, a topological quantum field theory in 2 dimensions is not fully extended if you can only define in the source category the Bordism category of oriented cells. Either there are 2 cells or 1 cells, but you can't define the 0 cell, that's why you say it's not fully extended, because you can't extend it to the point. So why is this important in relation to physics? Is because you can think of a theory where a physical theory, a quantum field theory, that you have full control of as a functor, just as these functors that I define here, that are such that it's enough to define that functor at one point to be able to define the theory everywhere else. So this is crucial because it means that you can just shrink the extended dimensions of your theory to a point, and all the knowledge is going to be encoded in that point. And if you know how to define the functor on that point, then you have all the information you need. conceptually it's quite, you can actually think about it, but if you actually think that the extended dimensions have at the same time objects, morphisms, because they are actually extended objects, okay? So you think of the extended two cell, the loop that separates the extended two cells and the points. If you shrink all that to just one point, then that point is going to carry all the information. Of course, the definition of the partition function, once you've shrunk the dimensions to 0, it's going to be much more complicated. But if you know that, then you're able to define that theory, and all the correlation functions that would result would be known. So this is why this is something important to bear in mind, and that we would like to achieve, to define any quantum field theory in any dimension. But of course, you can control this even visually much easier in 2D. So this is why we use this two-dimensional perspective. Now, a non-fully extended TQFT can still be extended to a fully extended topological quantum field theory, as long as the non-trivial part that will result from the shrinking of the loop, if you can identify that non-trivial part, that would be some kind of algebra that lies at a point. If you can identify that with the endomorphism of the identity of the new theory, then you would still be able to go back to the theory that you had before. So it will be a fully extended one. So why am I saying this? Because remember when I told you, I think it was the first lecture, or maybe the beginning of the second, I said that an absolute quantum field theory is one such that you can define three functors at the same time, and they are all equivalent. So one was the fiber functor, one was the moment map, and the other is the Dreamfield center. So if you know one of them, you know all of them, if the theory is absolute. So it's totally equivalent which one you pick. I said the moment map is the one that allows you to map a subcategory in the symmetry TFT, a subcategory of defects in the symmetry TFT, to a particular algebra. And that algebra is the algebra you need to gauge away in the which means that it tells you which is the subgroup that you need to gauge away from the global symmetry group that acts on the mother theory. So that choice of the subalgebra that you're going to gauge is exactly equivalent to saying that in this non-extended topological quantum field theory, you shrink a loop, and the algebra that sits at that point is exactly the algebra that you've chosen to trivialize in the fully extended topological quantum field theory. So under that identification, then you can rebuild what there would be the fully extended topological quantum field theory. So it will be equivalent to saying you do an ungauging procedure. Okay. So that was just to conclude the part that we discussed last time. Okay. Now we turn to the supersymmetric theories. So why are these important? I just said before in the introduction of this lecture, and I still want to stress that they are important, especially because they have a lot of mathematical understanding, which makes contact with what I've said before. So the first theories that we're going to start with are these so-called six-dimensional n=2 superconformal field theories. So if you are from a pure maths background, you might have not heard that much of them in this language, but they are also known as theory X. And there's a lot of work by Ben Zvi, for example, that has done this in representation theory. But they are crucial in physics, especially if you try to use this top-down approach in model building. So we will see now how to deal with this theory in the context of symmetry topological field theories and dimensional reduction, which subsequently leads to supersymmetry, partial supersymmetry breaking. Okay, and we can actually see with a concrete example at work the things that I described in the previous lecture. So this is just a map for you to bear in mind. It's a subset of another map that was presented by Gregory Moore, who's a physical mathematician, in a lecture that he gave. He has some notes that are very inspiring. I would suggest you to go through them, but it's a very long article, but it's very nice. And it gives you a description of how to go from the higher dimensional theory, which is highly supersymmetric, 6 dimensions, n equals 2, superconformal field theory, to different theories. So here I said this is a very oversimplified diagram, but just to give you an idea. So if you start from a 6-dimensional superconformal field theory, you can choose to make this theory live on a 6-dimensional manifold that is split into the tensor product of a 4 manifold and a 2-dimensional manifold, which is a Riemann surface. So according to the choice of the genus of the Riemann surface, you're going to end up into 2 different setups, which are the ones that I show you here. So if you choose a genus 1 Riemann surface, so it's the torus, then if you dimensionally reduce on that torus, you end up having another theory, which is a 4-dimensional n equals 4 super Yang-Mills theory, which is also known as the setup where you look at Langlands duality, which is a particular kind of electromagnetic duality that arises. We're not going to look into much detail into the Langlands dual. I don't think I have the time to do that, but this is just to give you an idea. On the other hand, if you perform a dimensional reduction on a Riemann surface with some arbitrary genus, then you end up having what the so-called class S theories, which are 4D n equals 2. So it means it's got less supersymmetry than this other theory that you've dimensionally reduced on the torus. So you see different patterns of supersymmetry arising according to the choice of the compact manifold that you compactify on. And this is a feature that is typical to all compactifications when you go from higher dimensions to lower dimensions. And it's the reason why then in string theory, when you have highly supersymmetric theories, you dimensionally reduce on Calabi-Yao's, for example, which would be threefold, so it's 6 dimensions in that case. And you end up having 4-dimensional theories that have fewer supersymmetries. And then you need to study how to break furthermore that supersymmetry. So this is just to give you an idea of how this works from the point of view of category theory, how this dimensional reduction works. So we're going to see this from the point of view of symmetry TFTs and category theory. So first of all, let me state that there's a theorem that which is called the Milnor-Moore theorem, which tells us that the 6-dimensional superconformal field theory can live on the boundary of a 7-dimensional theory. So here I call XG, G, in this case, it's a math frac G, which means the algebra that defines the superconformal field theory. This is part of the data of my superconformal field theory. And alpha G is the bulk 7-dimensional theory that is the topological data of my 6D n equals 2 superconformal field theory. So the important feature of this theory, as you can see, is the lack of the topological boundary that we would have if this were the usual symmetry TFT picture. Now, this lack of boundary condition is crucial in the sense that it tells you automatically that this theory is non-Lagrangian. So the reason why it's so is because you can't define the boundary conditions of the fields that live in the 6D n equals 2. So that's why it's not a Lagrangian theory. You can't specify the field content, but even if this seems as something that is undesirable, at the same time, it gives us a lot of freedom because it tells us that it gives us a way to choose how to select those boundary conditions. So this is basically the essence of why this theory is so important and why it gives us that diagram. So, that's why you have all those theories that come up and all the dualities that arise are all coming from the fact that this theory does not admit the topological boundary theory here that gives us, as a top-down approach, the boundary conditions of the fields. So bear this in mind, okay? And the first people to address this as a relative quantum field theory were, first of all, Witten, and then followed by Fried and Telemann, that wrote a paper together about relative quantum field theories. And used this as one of the examples they provided to describe this setup, together with the sigma models and gauge theories that I described in the previous lectures. So now we delve into much more detail of what this theory is. So this 60 n equals 2, I said you can think of it as being defined on some six-dimensional manifold, say Y, and I split this into two parts. I say X is the four-dimensional part, and sigma G is my Riemann surface, okay? And what I know about this theory is that it admits six-dimensional self-dual fluxes that belong to this cohomology that I can split. Okay, I can split it into an H1 and an H2. You see that H1 lives on sigma G and H2 lives on X. Okay, so I split it according to the splitting of the manifold I've chosen. So I said already here that this is non-Lagrangian, and the reason is because you can't fix the topological boundary theory in the picture that I showed you before. Okay, but at the same time, we can choose to dimensionally reduce. So if we choose to reduce on the Riemann surface, we end up having a four-dimensional theory, which can admit instead a Lagrangian description. Okay, so that's why we're interested in that, and we can look for a particular partition function in that case. But to do that, we need to select and specify additional data. So in particular, we need to identify a maximal isotropic sublattice of the H1 that lives on the Riemann surface. Okay, and this is because we need to define this other object, which is the tensor of this maximally isotropic sublattice and H2 on X, because this gives us the lattice of H3 on Y. So this basically is encoding the information of the fluxes that will live in the resulting theory once we've dimensionally reduced on sigma G. So to do that, we need to fix L and the complement of L, which is this L perpendicular, which is basically the quotient of H3 that results with modded out by L, which is this curly L here. And this parameterizes, this perpendicular L parameterizes all the possible partition functions of the resultant four-dimensional theory once we've dimensionally reduced on the Riemann surface. So all this that is said in words can be written down in a very compact way in terms of these expressions that I will now describe. So given that you can't fix the boundary conditions of the three-form fluxes in the 6D theory, you don't actually have the notion of a partition function, but you have something which is called a partition vector. So this is why instead of using just Z to denote the partition function for the 6D theory, I use this bra notation, which means this is actually a vector. Okay, it's like a state, but it's actually a vector. And this vector is telling you that you have unspecified boundary conditions. And these unspecified boundary conditions are labeled by the choice of the curly L perpendicular that I defined above. And you're going to have basically a sum over all these possible states that are labeled by curly L and its dual. And the coefficients in front are going to be instead the partition functions of all the possible resulting four-dimensional theories that you would obtain by dimensional reduction. So this is overall, this gives us a partition vector, and the dimensional reduction would select a particular coefficient as the resultant partition function of the 4D theory. So this is what this slide is basically telling us. Now, this is again something I already mentioned. So the Milnor theorem states that if we start with a Lie algebra in a 6D n equals 2 theory, then we're going to end up having a seven-dimensional bulk that encodes the necessary braiding and ribbon structures that correspond to the categorical that encode all the spectrum information of the six-dimensional theory. So in practice, what this means is that we can define an action in the seven-dimensional bulk, which looks like the following. So we have the first term, which is basically, you can recognize it's the usual Chern-Simons term you would have. I showed you a Chern-Simons example earlier on, and in 3D. This is in 7D, so C is going to be a 3 form. And you're going to have two extra pieces of data here that I added. And these two extra data are basically nothing but the electric and magnetic charges that I choose. Okay, these Qs, Q and Q prime, are going to be the charges of objects, extended objects, in this case, three surfaces, because I'm integrating over M3 and M3 prime, that create a hop link in the bulk symmetry TFT. So if you remember when I defined the charges last time, I said that we could identify, for convenience, charges physically as, we can split them as, we can think of charges as being different superselection sectors of an overall category, which is the category of defects. Now, I said, for example, you can think of the electric charge as being point particles, fluxes as being the magnetic charges, and Hopf links as being dionic objects. So in this case, in this picture, I'm encoding a Hopf link because I choose these two charges to be the electric and magnetic charge, but the two manifolds, M3 and M3 prime, I'm choosing them to be Hopf linked with each other. Okay, so this is a higher dimensional version of the Hopf link I showed you earlier that gives us the Braden structure, which is needed to encode the non-trivial categorical data of the theory that we want to describe in 6D. So all that I said in words here just maps to the definition of Wilson surfaces, because in physics, in these high dimensional pictures, usually the Wilson surface is associated to some kind of electric charge, and then you would have the Toft surface, which will be the magnetic one, and then you can admit dionic objects by pairing Wilson and Toft objects together to build something that carries a dionic charge on it, so it's both electric and magnetic. So for the case of electric, purely electric case, I can define this Wilson surface to be just the exponential of the first term that I had in the action. Remember, I had Q integral over M3 of C. So this is just the exponential of that, and that is by definition the Wilson surface. And this Q is going to be an integer, and M3 is just the manifold that the submanifold in the bulk 7-dimensional theory that I define. So I can choose these manifolds M3 and M3 prime to be suitably creating a Hopf link in the 7-dimensional bulk that I call W7, and I can insert them in the path integral. So if I do that, then I can do some mathematical manipulations and denoting with the using Poincaré duality, I can rearrange the action such that it takes this form. Now, if I integrate out the field C and I impose this constraint, okay, I can define a 4-dimensional volume in this way, which is just a combination of the charges and the omegas of M3 and M3 prime, which implies that C needs to be this particular expression here. So in particular, the 7-dimensional theory ends up being a product of QQ primes, so the two charges that are carried by the two linking surfaces, and the link in between the two, which is just a coefficient, okay? And this thing is going to give us some kind of coefficient in front of correlation functions. So I'll show you in practice what this means. If I calculate a correlation function in between observables in this particular setup, this would mean that I take the expectation value of different Wilson and Toft surfaces in the bulk. So in practice, this means the following. I just write phi q of M3, phi q prime of M3 prime, etc. So this means that I know how these two manifolds are linking, so this term is going to be in the exponential of the action. Sorry, it's going to be in the exponential that defines the partition function. So when I write down this expectation value, I actually should think that there's always like an exponential of the action involved. So that exponential of the action is going to bring me this extra coefficient that I just bring it out. So I can swap, I can remove these these operators here, and just bring out this coefficient here, which is just a number, and I end up calculating the expectation value of the resultant things that remain here to be defined. In particular, if I didn't have anything else here, this would just be the expectation value of the identity, which I know to be already the partition function because I defined that in that way. So this is just an example, okay? But I could have had many other phi's here on arbitrary surfaces to calculate. So now that we explained this, I told you that we can find this particular four-dimensional manifold that results from calculating the equations of motion, basically of C, and those equations of motion are going to give us constraints on the three manifolds that define the boundary of the four-dimensional manifold. So I said V is basically the four-dimensional manifold that results, sorry, not this V, the other one. The one that I defined before was a four-dimensional manifold, as I said. But then you can split the seven-dimensional manifold that you have in the bulk into two parts. One is going to be the X4 that you want as part of the dimensional reduction of the 6D theory, and the other is a three-dimensional manifold that I call VGN. And this VGN carries basically the genus and number of punctures with it, okay? You can think of this three-dimensional manifold as being the bulk of the Riemann surface on which you are dimensionally reducing, okay? So for any Riemann surface, there are many different inequivalent three manifolds that have it as a boundary. So one of these examples are the handle bodies. So we can choose a particular parameterization of the Riemann surface, which corresponds to identifying different generators of the H1s that we know to that we've, as I mentioned before, they are defined on the Riemann surface. So in particular, we need to define the meridians and the longitudes. So these are the two sets of generators. Since the Riemann surface is it needs basically two times G generators. We split the generators into two equivalent subsets. One is that of the meridians that are parameterized with mu I, and they come in G number. And the other are the longitudes that are parameterized with lambda I, and they also are in G numbers. Okay, so with them, basically, I cover all the generators of H1 on the bulk VGN, which is the bulk where sigma G is the boundary. Now, why do I do this? Because you can think of this, if you think of, you start with an arbitrary surface with an arbitrary genus number, okay? And you want to because I'm doing this because I know that I want to dimensionally reduce on the Riemann surface. So I want to shrink this surface at some point. But to do that, I also know that the Riemann surface carries important information about the field content that will result in the 4D theory that I'm going to end up with. So I need to parameterize the surface before shrinking it, because that parameterization is going to come with a particular choice of the boundary conditions of the fields that live in the 4D theory. So once I've defined the meridians and the longitudes, and I specify on which of the two subsets I'm going to perform dimensional reduction, that will lead to a particular choice and definition of electric, magnetic, and ionic charges. So we're going to see this next, okay? So all that I said before, basically, again, we see L. This is how I parameterized an element in H1 of sigma G. Here I just consider sigma G without punctures, okay? Just for ease of calculations, okay? But you can generalize this for the case where punctures are also added, okay? So the handle body, I said it's specified by a particular choice of meridians that we denote with this VG0L. So given this VG0L, we have a multiple choice of longitudes for the particular meridians that differ only by shift, okay? And they satisfy some constraints that are these normalization conditions in between them, between meridians and longitudes. So the 7-dimensional Chern-Simons theory on the handle body can be formulated by starting with the definition of the fields that are as follows. So we have the B's, Bi and B hat are basically related to electric and magnetic pair charges, okay, or fields in this case, okay, electric and magnetic fields, think of them in that way. So they're dual to each other and they are defined as contour integrals of the three flux C on respectively the meridians and the longitudes. Okay, so you see that. So basically, you can think that if I shrink on a cycle that is associated to an electric field, I'm not going to have that particular electric field anymore in the dimension reduced setup. And vice versa, if I shrink on the one corresponding to the magnetic field, I'm not going to have the magnetic field in the end. Okay, but these two are, if I assume that they intersect in some way, so I know that the longitudes and I know that the longitudes and meridians intersect non-trivially because they create some kind of network on the surface. So even if I shrink all the longitudes and I end up just with the meridians are going to carry non-trivial information about the longitudes in the intersection points. Okay, and vice versa. If I start with the by shrinking the longitudes and I have just the other way. I don't know. If I shrink all the longitudes and I end up just with the meridians, I'm going to have still carry the information throughout the intersection points. Okay, so I'm not going to lose anything, and that is why it was important to have the hot flings to begin with. Okay. Now, so basically in practice, what I need to look at is how the extended objects that those hop flings, the three surfaces that defined the hop fling in the 7D Chern-Simons theory, how they're going to they're going to behave under this particular choice of longitudes and meridians. So the Wilson line, for example, is going to be something that is defined on a two-dimensional surface now, because I shrink over one of the dimensions of the Riemann surface. So if I do that, then I'm going to remove one dimension of the three surface. So I end up just with a two surface defect. And that you can also think of it as being just like phi calculated on the M2, which is the new 2 manifold, times mu I, which is the meridian that I've chosen to shrink on. So the corresponding defect is going to be an exponential of 2i over n. This is just the factor in front that comes from the Chern-Simons definition of the action. And the integral is going to be a contour integral over this 2-dimensional manifold of the field Bi. On the other hand, I can define the dual object by this phi hat on M2 as being instead phi on M2 times the longitude, and this is the one that I'm shrinking now. So this is going to be the exponential of 2 pi I over n integral over M2 of Bi. So if I can then take something which is like a more intricate thing, and I can use an intersection of both. I can take a suitably intricate setup such that I define a new object in 2 dimensions, which needs to carry an information of both. So I can have a resultant field, say this B, capital Bj, which comes with both labelings. You see, I've performed some kind of dimensional reduction that involves both the mu's and the lambdas. So this is why I would end up having this sum over j's of an inner product, a pairing in between the mu's and the lambdas, okay, because I know that they non-trivially intersect. So in the 4D theory, I know that we can calculate correlation functions in between these phis. So these phis live now in a 5-dimensional in a 5-dimensional symmetry TFT in the bulk, and they are at the bulk of a four-dimensional theory at the boundary. So in the four-dimensional theory, we want to calculate correlation functions, and those should be mapped to, or matched, let's say, to calculations performed in the bulk, which means correlation functions in between these phi's in the two-dimensional theory. So I can do that by, I can calculate the correlation functions and choose to suitably swap the order of the phi's at the price of adding some coefficient in front of the correlation functions, such as the ones that we've seen before, those exponentials. So basically, we can split the symmetry TFT and the resultant handle body that I explained before in two different regions. Okay, so in the dimensionally reduced setup. Okay, so these are basically the two regions. You're going to have some new variable y, which is basically the one where you that parameterizes the extension, and this is telling you that at some point there's a split in between what the 3D, this was a 3D thing, remember? So this is the 3D in the bulk of the two-dimensional Riemann surface. So I can split at some point in between having it internal and an external value. So this is in between splitting, considering this as just a unique three-dimensional manifold, or splitting it into a two-dimensional Riemann surface times an interval. So in pictures, this is what it would look like. So imagine this is for the seven-dimensional theory. I start with the seven-dimensional theory, and I dimensionally reduce on the Riemann surface. So this blue, in this case, I chose for simplicity just genus 1, okay? But you can have higher genus, it's fine. So I choose the sigma to be this, initially this, and I perform a dimensional reduction on sigma. So if I do that, I end up with a four-dimensional theory, which would be this slab, just the black slab on the right. But then I know that according to the parameterization I've chosen, the bulk of sigma is going to be this three-dimensional theory, which is still like three-dimensional external, but this is split now in between sigma. So this part here would be sigma times an interval, and the interval would be this dashed part. So I'll go back. We have, you see, there's an external one, which is sigma times an interval, and the other is just the internal, which is just a three manifold. So if I go back here, I see the bulk here, it's sigma, just translated, okay? Just imagine to transport this towards the left, and I have an interval. So it's sigma times the interval. And then at some point I hit some value where at that point I have another bulk, which is closed without any end here. Okay, so I don't have any boundary here. And this is, you can think of this as coming from the fact that, as I said before, you don't have the boundary conditions for the 6D n equals 2. Okay. Now, if I dimensionally reduce all of this all together, I dimensionally reduce on the Riemann surface, I end up having the 4D theory on the right, and this interface in between the two possible configurations of the 3D bulk of the Riemann surface end up giving me precisely the boundary conditions of the fields that live in the 4D theory. Okay, so this is where the dimensional reduction leads to having the topological boundary conditions for the symmetry TFT. So as a whole, the symmetry TFT would live in this bulk, this one that I'm pointing at with a cursor, and this is exactly the picture that I described in the first lecture. Okay, so it's precisely here. And now we can define on the two black slabs two states. One is the state that is associated to the theory that we want to study. It's a relative theory, the four-dimensional relative theory. And on the left, we have the topological boundary conditions that would give us a particular choice of the spectrum of operators that will live in the resultant four-dimensional theory. So this shows how concretely the boundary conditions arise naturally from a theory that doesn't have or doesn't admit any boundary conditions at all. So it also tells you that there's a way mathematically controlled to go from a non-Lagrangian theory to a Lagrangian theory, which is crucial for our purpose. So in practice, the bulk symmetry TFT in 5 dimensions is going to be given by this new Chern-Simons theory, where I would have, basically you see it's the same, structurally is very similar, but I have now a sum over all the genus associated to, so this is sum over the genus G, of all these fields that are the fields that are associated to the choice of the meridians or latitudes that I'm choosing to shrink to obtain the new 4-dimensional theory. And these would be the dynamical fields, of course, in the 4-dimensional theory, associated to the dynamical fields in the 4D theory. Okay. And this is basically what I already said before. So you're going to have the new Wilson lines are going to be defined on a 2-dimensional manifold rather than the 3-one, times a curve. And this curve, gamma, is basically a superposition of a linear combination of both the longitudes and the meridians according to how I've chosen them. And the coefficients in front of this linear combination are going to give me the charges associated to the particular curve that I define. So you see, I'm going to split the parameterization into coefficients that are electric or magnetic, and they come in G numbers, each one of them. And this is because to each genus you can associate a corresponding electric and magnetic charge. So this sets the convention that I choose for the spectrum of operators. Now, this is just an example of how I can write it in the case where I can write a generic, if I choose this parameterization, okay, which is both electric and magnetic, it means if I shrink on this gamma, this is what I mean with this notation. I mean, I shrink on this gamma, I shrink on something that carries both electric and magnetic charges on it. So I'm going to end up having an object, which is this phi m2, that is going to be a dionic object, okay? Because of that, I can write it down as, in this way, as a product of, I can split it into its constituent electric and magnetic contributions. So I'm going to have a product over phi's that are Wilson lines purely electric, and other phi's that are instead Toft lines that are purely magnetic. And as a whole, I'm going to have also coefficient in front that takes into account that these two are actually correlated to each other because I have that non-trivial definition of the gammas that are dionic objects. So the coefficient in front carries the information that E and M are for this particular choice of gamma are giving me a non-zero inner product. So if I didn't have this coefficient, it meant that the longitudes and meridians did not intersect in my choice of parameterization of the Riemann surface. So I would have just had a factorization of the phi's without the coefficient in front. So okay, let me just skip this for a moment. Okay, no, let me say now. So this gamma, this choice of the curve that on which I choose to perform the dimensional reduction on the Riemann surface, and that gives me a particular spectrum of operators. Gives me also the definition, an actual definition of a surgery defect. Okay, and we're going to see this next because basically, as I mentioned before, this shrinking of the gamma gives me a choice of the spectrum, which means I choose the boundary conditions and I choose the topological boundary condition in the symmetry TFT. So to do that, it's like saying that you choose a particular moment map and you project the gauge group of the symmetry of the global symmetries in your theory to a particular subalgebra. So that statement that seems very abstract comes down to being very concrete in this language, because basically you can define a map in between a Wilson line, which is this Wilson or Wilson surface in this case, defined on some particular choice of n vector. This n vector, remember, it's the set of all electric and magnetic charges that are carried by this object, defined on M2. I can map this to a Wilson surface, sorry, on the same manifold, but now the labeling of the charges is going to be this Fn vector, which means that I accounted for the action of the shrinking of gamma on the charges. So this action defines a functor that I call this curly C, curly CF, defined on the four-dimensional theory, which gives me an interface. So pictorially, you can think of a defect. This defect lives on M2 as being just the surface of the cylinder on the left-hand side. And this would be my Wilson surface. And at some point, I act with this operator, CF, and I get the theory that has instead this other Wilson surface defined on it, which is labeled by F acting on N. So on the same surface M2. So this interface is actually an interface that arises in the bulk, and this is usually called the gauged algebra. Okay, this CF is like a gauged algebra. We'll see why. So you can perform now some kind of fold. You can fold the right to the left, and you end up having a resultant object, which would be labeled by the identity minus F acting on the vector n. So at the boundary now you're going to still have the same defect you began with, which implemented this gauging, and the resultant object here is basically you can get back to the identity if F were just the identity, or you can get something which is like a resultant Wilson surface that is non-trivial. So why this CF is important with relation to other things we said before, because so this CX admits some explicit expression that I wrote here for convenience for you to see. So as I said, it's implementing a morphism in between Wilson surfaces. So I can define it just as being a superposition of all Wilson surfaces that you see here that are calculated on 1 minus, so the identity minus F acting on M2, because I can trivialize this in the case that F is just the identity, this would just be giving me C that is just trivial. Okay, it wouldn't be anything, it would just be 1. But the fact that F is different from the identity gives me a Wilson surface that is actually something non-trivial. And this thing carries some weights that are given by these cohomologies in front that come from, if you remember, similar expressions. We've seen them when we discussed relative field theories in the context of gauge theories. I think it was the first lecture. Yes, definitely it was the first lecture. And we saw how to turn relative to absolute gauge theories, and they had exactly these kind of coefficients in front. So this is exactly that, okay? And the thing that we have here on the right, is basically something like the sum over the relative theories that we saw in that case, okay? So this is carrying that information, and I'm performing a particular choice here of the F. So a particular choice of F is like selecting a particular subgroup in the gauging, in the gauge group, and gauging that subgroup away to give me the resulting defect. So this CX4 is basically my new notion of the identity. When I told you before that I select a particular moment map and I project on the corresponding I project on the subalgebra corresponding to a particular sub-n category associated to the defects I'm gauging. This CX4 is exactly that definition of the algebra that I'm gauging. So you see, in fact, that you can try that if you try and take the inverse, the orientation reverse of CX4, and you tensor it with CX4, you end up having the identity. Okay, so it works. It actually tells you that C is just the identity in the new theory, in the gauged theory. And pictorially, you can think of this as just being this black line that I have in the middle of the symmetry TFT. So we saw this, I think, last lecture when I showed you that the gauging in terms of in categorical language means that you can flood the symmetry TFT with a network that I called the categorical idempotent that you define once you've defined the subalgebra that you want to gauge. And that categorical idempotent, by definition, can just be any arbitrary network you want. And because it's an idempotent, you can rearrange the points such that they are just a unique line, just as that, you see. But this could have been any arbitrary random thing, okay? This is just, I'm using the idempotency property to get back to this. Now, pictorially, this tells you that this defect that runs inside the symmetry TFT like this is just trivial for the new theory. So it's just the identity for the new theory. So you can just cross here and it's not going to affect at all the defects. If it were non-trivial instead, that would be this theory, this picture would just be wrong, okay? It wouldn't make sense because as I told you before, the bulk here is just topological and the boundary here that is also topological, this rho, altogether gives you the topological information of the result in absolute theory that you would get by dimension reduction on this interval. So whatever you have here in the bulk knows what lives on the boundary on the right. And dictates the field's boundary conditions of the resultant theory. So this is telling you basically that this gauged algebra is giving you the definition of the new identity. But we have, as you see here, we have a particular expression that gives us what the identity is and what are the corresponding choices of boundary conditions that define where that identity comes from. And you see, it's highly non-trivial getting it from this with respect to just saying this object is the identity to begin with. Okay, so you see that you can appreciate actually the depth of where the notion of the identity comes from this picture and how it's related to the choice of the spectrum of operators. Now, another thing that you could do instead is to perform something else, which is called as double gauging. And you perform a double gauging in the case where, in the case where the gauging is double, and where there's a non-trivial overlap in between the two subalgebras that you are gauging, and the non-trivial overlap is giving you a resultant defect, and the condensation, the idempotency, yes, the idempotency gives you as a resultant defect in the bulk something like this. So you can think of this picture in the middle as coming from having two different floodings, two different networks, and there's a splitting in between the two. And then what you do, you can say, I choose one of them to be my reference setup. And as a consequence of that, you perform this same thing that I did here. I say, I choose one of them to be the identity, and the other one is going to be everything that results after removing it. So I'm still going to end up having something like this, but not quite the same, because I'm going to have now on one side, I'm going to have something which is similar to the thing we have on the left, but then the other side, you see it's empty, which actually tells you that there's something different that's taking place here. And that something different is encoded for by this defect that non-trivially ends in the bulk. So having a non-trivially ending point for a defect in the symmetry TFT, it's something that is very important because it tells you that you can't define a fully faithful fiber functor in this context. So, and this is the source of why it's important to go beyond all these setups that I showed you up to now, which are like the starting point of this method, but actually it's not the full picture. So this thing turns up being quite common in some physical circumstances that are needed to be taken into account. So this extra dot here is actually telling you that if you compress this interval, you end up having two theories. in the absolute theories that are split by a non-trivial algebra that is carried by this defect. That non-trivial algebra is going to be like a defect that might carry non-trivial duality information in between the theories that you would like to study eventually. Okay, so this also maps to having, as you see here, on the left, you can turn this, you can push this to the boundary, to the topological boundary, because this is being topological, you can move it everywhere you like. It's going to be giving you two different boundary conditions that are different from each other. You see, I denoted them by epsilon and rho. So actually, you're going to have two different theories because the two topological boundary conditions are different. So different field content, different theories. And they are non-trivially related. So there's no, in this case, I'm choosing it such that they are not related by a gauged step, one from the other. So they are highly non-trivial. So this is basically in expressions what I already said in words, so I'm not going to repeat it again, and you can see this in detail, but basically you see that I denote, I use a shorthand notation here to rewrite what I had before in the definition of C using the S matrix. So I use the S matrix and the notion of, I use these new labels A, vector A, to denote the representations and conjugacy classes, which are basically defining the electric and magnetic charges. So you see here, I'm using all the machinery I've explained in the previous lectures in a particular example that you can look in depth. And in the case, so going back to this, when in the case where the defect is in the bulk, like this, if the defect ends in the bulk, then this algebra, as I said, that dresses this point defect, is actually going to give me some fusion rules that are non-trivial. So instead of having this fusion rule that I said, if you compose C with its orientation inverse, I'm going to end up having the identity in the new theory. This is not going to work now. So if I take the tensor, the tensor product in between n, which I defined n to be this theory that lives in the end point of the defect in the bulk. If I tensor it with its orientation inverse, I'm going to end up having a non-trivial algebra that dresses this defect, and this is going to live in the four-dimensional in the boundary in between the two four-dimensional theories that I separate in the resultant absolute theory. So essentially, you can think of this thing as coming as being like some kind of relative gaugeable algebra in the absolute theory. So if I take this this four-dimensional theory, I can like zoom out. So this I said it's an algebra in a 4D theory, so I can think of gauging I can think of this algebra as coming from some previous steps that are we will see later. Maybe it's already not already here, but in a few slides' time, we're going to see this explicitly, that this algebra on the right, this AX4, comes as something that you would get from by gauging a particular algebra in two different ways and composing them together. So I will explain this diagram next, but first I will take, I think, 5 minutes of break. And if there are questions, think about them, and it will be a good time to ask once we resume. So Daniel, are you okay? Okay. Okay, so this is just another picture of what I said. Just, you know, these are all pictures that I added to the slides, hoping that people will find them inspiring. So you will see all these also in the papers that I wrote and also in the references that you will find in the papers. So this is basically in pictures what I said when I discussed about the dimensional reduction and the double gauging. So in the case where you have a defect that ends in the bulk, then you see that if you compress the interval, you end up having two theories, these two blue lines that are separated by a defect here in the middle. And this defect has non-trivial fusion rules. So if you fuse NF with its orientation in reverse, you end up having something which is not just the identity, which means that if you try to go from one theory to the other, you can't do that just by performing a gauging procedure or an ungauging procedure. Okay, so this gives rise to non-trivial not interactions, I won't use this term, but some non-trivial relations in between these two theories that you would like to study. Okay, for example, you could construct S-duality using these things. Okay, so it's that's why I'm saying that these machineries are important, because you can build duality pictures with this setup. This is again the same thing that I explained above, but I'm not going to say it again. And so if you look at the configuration I said, when you compress the overall symmetry TFT and you end up having two different theories, the two different theories are going to be they're going to be labeled by different boundary conditions because of the defect that lives in the bulk. And consequently, each one of the two theories is going to be associated to some different category, so that I call C and D, category of defects that fuse and have morphisms, etc. And the corresponding defect that lives in between them is going to be, I'm just going to denote the non-trivial algebra that addresses this defect that I call A and carries the two indices of the boundary conditions that I fixed for the two absolute theories that live on the two sides. Now, to appreciate where that algebra that sits in between lives, you can think of it as coming from this picture that I have here. So you start from a mother algebra, curly A. Before doing any gauging at all, you assume that you have just this algebra, and then you perform two different possible gaugings. Either the one that gives you the category C that lives in one absolute theory, and another gauging that gives you another category D that lives in the A2 theory instead. So each one of the two steps is going to result in having a different boundary in between the two algebras. So if I put them together, I squeeze this green part to be just zero-dimensional. If I squeeze it, I basically end up having this resultant algebra that lives in the junction of these two, of the blue and the red line. And this is what I call A, with the two indices on the two sides, A1 and A2, that tell me I'm keeping track of the two algebras that were used to perform the gaugings to get the two absolute theories, C and D. So this thing is basically encoded in this diagram, which is called correspondence. So this diagram is called correspondence. And you can see that I start from the same theory, this A for D, and I have two algebras that embed in it, this A1 and A2. But A1 is paired with the notion of a certain two category, and A2 is paired to another two category D. So as a whole, I can think of this composite algebra, A1, A2, as actually being the relative tensor product with respect to A of A1, A2. So the relative gaugeable algebra is basically a fusion tensor category. So this is just more details for those of you who are interested. And you're going to have, it's going to be defined in this way. Where you're going to have morphisms and one morphisms and zero morphisms for objects and relations between any pairs of elements that live inside the two respective categories. So I can take this algebra actually knows about how the two categories interact with each other. Okay, so this is why I'm writing this down. So now, basically, the main message of this part is that an open question is that of looking at what happens when you have multiple absolute theories that are separated by non-invertible defects. This could give rise to potentially n-tuples of dualities in between them. And it's nice to study what is the relation in between the algebras that separate these theories, because they encode how the theories are related to each other in turn. But the crucial thing I want to stress is that this all comes from knowing what is the underlying algebra of the theory that lives, of the theory that that you choose to begin with. So in our particular example, before we had the 60 n equals 2. So you had that, I mean, you were given, that was given, and you have a particular algebra. But say that you have some other theory that is not supersymmetric, you still want to find, to study how that theory is related to some other theory. You can say, I assume that I know the respective algebras that give me their corresponding boundary conditions, and I want to study the defect that separates the two theories as absolute theories. So you can construct some highly supersymmetric theory, or sorry, I won't say that, but you can construct some higher symmetric theory, let's say, and that theory is going to have a bigger algebra that is associated to its symmetry group, and that symmetry group is going to encode all the possible realizations of different theories that you're studying. So then you see there's this notion of going from the theories specific theories to a broader theory that you would like to find. Okay, so this is basically very much similar to this trying to embed effective field theories into higher symmetric theories. So this is why this thing is very appealing from the point of view of string theory, especially. Okay, but this is something that still needs to be developed. This is why I'm saying that. Okay. Now, this is just a brief digression on cohomologies, because where we're heading next, so I'm not sure, maybe this is probably not the right moment to talk about this. Maybe I will come back to this later. Let me first go to this before going to that. So let me see where we are now. So I showed you a particular example, the one of the 60 n equals 2, how dimensional reduction works and how symmetry TFTs are used in that context to identify a particular absolute theory that is characterized by fewer supersymmetries, and how you can potentially construct duality interfaces that separate them. But those four-dimensional theories are very particular. They are four-dimensional n equals 2 that are also called class S. Now, these theories, you can use some kind of quiver descriptions, for example, and this is where we are actually. The setup of quivers is very important. For those of you who don't know, quivers are diagrams that are used to describe gauge theories. So, for example, there's also the standard model quiver, and there are works that have explained how to embed that in string theory. So, in particular, I'm talking about the minimally supersymmetric standard models, which is n equals 1. Okay, so there's still some amount of supersymmetry in those descriptions, but it was found a way to embed them in string theory models in type 2b. So, with that in mind, you would like to see how to be able to match that description to this. Okay, so now I'm going to show you that for the case of quivers, where you have this gauge theory, these gauge theories expressed diagrammatically, you can actually assign a functorial description that allows you to bridge that description to the one of the symmetry TFTs. Okay, so this is what I'm going to head next. So I'm going to show you in between this lecture and next time, which is tomorrow, I'm going to show you how this quiver description can be mapped to the functorial nature that I've shown you before. So this is basically the essence. I hope that this is going to be the main takeaway of these lectures, okay? And the reason why this course was supposed to be meant to inspire you in addressing particle physics in the language of category theory. So what we're going to deal with now is the two-dimensional topological field theory description of these quivers, but we're going to start first with the Morse-Segal setup. So why am I doing this? Because there's a big part of literature here that I'm not quoting, but the 4D n equals 2 that I showed you before how to deal with the symmetry TFT is can be described by using two-dimensional topological field theories, and this was work done by Gregory Moore and Yuji Tachikawa around 2012. And their work was mostly physical. It's a physics paper they wrote, but their work was motivated by a previous paper by Gregory Moore and Graham Segal, which is a maths paper, which is meant to start off describing the mathematics, especially the K theory, underlying D-branes in string theory. So you see that there's a big relation here with the motivations of this work in identifying the embedding of effective theories in string theory. So D-branes are basically a generalization of gauge theories for string theory setups, and if you're able to define the D-branes living in a particular theory, then you're basically done. You know everything about that theory, you know the operators. And so you see there's this recurrent idea that just as I mentioned before, the charges, you know, the spectra, it's exactly that same idea, identifying the D-branes. And in string theory, this is also known as the open sector. Okay, so open sector, open string theories are also known as, when you talk about D-branes, you talk about open strings, because you can imagine as open strings as ending on the D-branes. And they are complementary to another picture of string theory, which is closed strings. Closed strings are instead just two-dimensional things that span one space and one time dimension, and they live on the world sheet. So they give you basically the source of where to start to construct the D-branes. So you would like to be able to identify, once you know the closed string setup, the particular corresponding open string theory, which would tell you automatically which would be the charges of the D-branes that live in your theory. So you see there's this relation, just as I said before, identifying the brain content, okay? And this can be done in a functorial way. And that functorial way was first addressed by these two researchers, Gregory Moore and Graham Segal, in the language of Bordism operators that I will now try to start describing, okay? Most likely I won't finish this topic today, but I will anyway start now. So so they address this in the context of cochain level theories, because cochain level theories are essentially the same as the 6D equals 2. So 6D equals 2 is an example of a cochain level theory that you can actually describe with this method, okay? They are a generalization of this open-closed TFT constructions. And as I said, this is what I already said, they are enable you to determine the D-brane content arising from a certain closed string theory background. So let's start from a finite dimensional commutative algebra over some complex numbers. And you see that each one of these terms that you sum over can be split in turn into two parts, where this EX is an idempotent and MX is a nilpotent ideal. So C is a Frobenius algebra. And so if this is Frobenius, then CX is also Frobenius. So you can take the semi-simple case, and in that case, the idempotent would just be trivial, and you end up having just a sum over the E's. And this sum is such that if you combine E with itself, you just get the identity times epsilon as a definition of idempotent. Now, in Moore-Segal, you basically can define for any pair of boundary conditions, because you have, I remember this is the closed open string correspondence. So it means I had a picture about this, I think first lecture, I showed you the functorial prescription of string theory. If you go back to those slides, you will see that I had a picture where I had 4 red circles, and I defined a cobordism in between those 4 circles that was some kind of Riemann surface with a genus, a non-trivial genus. And that cobordism, I said, that's exactly giving you the source of a 2 category, which is a functor that maps to the open string sector. Now, this is exactly in expressions what that picture tells you. So you can start from different circles. Each circle is basically carrying some information about the field content. So it's like the boundary conditions of the fields that live in the bulk. So for any pair of boundary conditions, I can define them just as A and B. The corresponding cochain complex for a semi-simple category is defined in this way. So you have this O is basically defined as the sum over all possible x's of the endomorphism of this W, which is a vector space associated to every idempotent E. And O carrying two labels instead, A and B, would be just the sum over all the homs in between W's labeled by A and B, and summing over X. Now, a cobordism operator would map from a certain number of circles to a certain number of other circles. You can think of them as being like incoming and outgoing particles, okay, like in scattering amplitudes. And this bordism operator is actually, if you go back to that picture I had the 4 circles in that case, and 4 red circles and a blue surface, a blue cobordism in between them. So U would actually be the blue cobordism in between the circles, and I would have, in that case, 2 ingoing circles and 2 outgoing circles. So QMP in that case would just be equal, okay? But they can be arbitrary number. And these cobordism operators are labeled by obviously the Riemann surface that I have, the surface sigma, and by some additional structure which is called the conformal structure. And this is important to be accounted for because there's a big difference whether this is non-trivial information or not, and we will see this probably next time. And so, in fact, as you change the conformal structure, this maps to this map here, basically. So the target now is going to be omega of m sigma c tensor product q, where this m sigma is going to denote the moduli space of all conformal structures on the cobordisms. So now, this is basically a picture of what quivers look like if you've never seen them before. So quivers are basically graphs showing you how things are related to each other in a theory, in a physical theory. But they're also used just as purely mathematical objects. But in our purpose, we're using them as from the point of view of gauge theories. Okay, so you have nodes, and nodes are associated, but are usually conventionally denoted by these circles. Circles are related to the gauge groups, and then you have boxes instead that define the field content. So you're going to have one node for each gauge group and one box for each type of field particle that, color that is carried by particular particles. So that they are defined by this Dinkin diagrams. You have them of the AD type because there's A type, which are they come in displayed in rows like this, just one row with many circles. And then you have D type that instead is just displayed as a chain, and then it ends with this bifurcation at the end. And then there's E type that are in this way, they are either E6, E7, or E8, and they are arranged in this way. As you see, they are six nodes, 7 nodes, and 8 nodes. Okay. Now, I know that Nakajima gave lectures, so I'm not going to go into depth of this, but just for completeness. So Nakajima varieties are the ones that are actually going to be addressed in this from this point of view in what I'm going to deal with. So basically, you have this in this particular picture. You can see you have one node and with a certain gauge group, and then you're going to have a color here carried in, and the information is in this box with the flavors. Now, you take the linear space of representations, and you can define the corresponding moment map. And this is something that is well known. I already discussed about this before. But if you take then you have two different possible types, okay, of outcomes. You can either take the quotient with respect to the gauge group of the inverse of the moment map at 0, or you can take it once you've selected a particular character. Now, the difference in between the two is that the first is called the affine Nakajima variety, and it's in physics also known as the Higgs branch of the quiver. And the other case instead, where you fix a character, these are quasi-projective. And there's a map that maps the one to the other. It's like a resolution of the singularity. But we're going to see that for us, this one is going to be quite important. So the Higgs branch is going to be important in the rest. So, okay, this is just extra material. The gauge group, you can take it also to be some tensor product of different gauge groups. You can define a non-trivial character and a posomorphism that maps in between basically this is the resolution I was talking about before, that maps in between the two. Now, here we go to the Morse-Segal turned into the picture, the physics picture that we discussed before. So I said before that the Morse-Segal is used as a mathematical preliminary, I would say. They also state so. They say their formalism is just the beginning of a mathematical understanding of how to describe D-branes in string theory, okay? They also claim that their picture is not complete, but it's the starting point of this program. And after, I would say after like 13 years, Moore and Segal developed this in the Moore and Tashikawa developed this in the specific case of 4D n equals 2 superconformal field theories that are exactly the theories that I described before in the context of symmetry TFTs. So they defined these theories as two-dimensional topological field theories. What these two-dimensional topological field theories look like, they are, as in this box, they are a map from a Bordism 2 category to a holomorphic symplectic category, holomorphic symplectic manifold. So basically, you see this is reminiscent of what I discussed at the very beginning today, which is the difference in between fully extended and non-fully extended topological field theories. So in the topological order case, we saw that we had a cobordism here of a two-dimensional topological order, and how it was important to be able to shrink the description to a point to be able to define partition function. So in this context, we see that what this means what this two category structure means is the following. The objects in this Bordism are going to be circles. And the reason for that is because remember that this language is used to map the closed string to the open string. So I want to go from closed string theory to D-branes. And this is exactly what this map allows me to do because the objects are closed strings, so closed circles, and the open objects are going to be the D-branes. So the result of the action of this map on the closed strings is going to give me the D-branes. Now, so you see here explicitly the closed string, it's a circle. It's going to give me the gauge group, complex reductive gauge group, GC. And if you act instead with G on the one morphisms that live in the Bordism category, this is going to give you a set of different operators that are labeled by this complex reductive group. For example, if I take homomorphism of the circle, trivialize it to 0, I just get this particular operator. If I take the homomorphism in between two circles that are disjoint and trivialize them, I get the identity basically. And if I take the hom in between three disjoint circles and 0, I get another operator. Now in pictures, this is what they look like. So the Bordisms that are the one morphisms inside the Bordism 2 category would look like this. I have a circle, I trivialize it. I have two disjoint circles, I trivialize them. I have three disjoint circles, I trivialize them. And altogether, they give me the basic building blocks to construct an arbitrary genus surface. If you see, I can cap this. I can use U and I can cap one of the circles in W and I end up having V. Because by topological deformation, I can just, end up having the same thing. And this allows me to build also, I could also cap V on W and I would get a genus 1 with a puncture. and so on. So basically, if you use these constituents, you basically can reconstruct any possible punctured and arbitrary genus surface. Okay. So this is basically carrying a lot of information already about the notion of categorical dualizability. And this categorical dualizability comes because you basically can perform this full extension of the topological theory to the point. So basically, I can shrink this topology to a point without losing any information. Because you see, I can cap this W with U, and I would just get something that it's just a sphere, and I can shrink that without losing any information. But there are some cases where this is not true, okay? And for the moment, let me state that duality is categorical dualizability, is equivalent to stating that this equation holds. So if I compose U with W, I get the cotangent bundle of the complex reductive group, which is equal to this, to the action of the 2D TFT on the identity, which is basically giving me back the identity in turn, the identity in the target of the 2 category. So the main point is this, to stress that the categorical dualizability ensures the presence of the identity associated to a certain gauge group. Okay. And this relates deeply. You should think about this if it's not clear, but if you go back to the previous things we discussed, this is exactly what we saw in the context of topological orders and how this is related to fully extended TFTs and how to fully define a partition function on them. So if we go back to the notion of categorical gauging, sorry, just a second. So if we go back to categorical gauging, we see that the pattern that we described earlier, which is the flooding and selecting a particular subgroup and gauging that subgroup away, emerges here once more. Okay, so basically, the cotangent bundle of the complex reductive group is nothing but the identity that we define by defining a particular categorical quotient of the algebra that we begin with respect to a particular n categorical subgroup, and a particular n categorical structure of defects. So this notion of the identity that I stress to be coming from a topological composition of homomorphisms, this identity here is exactly equivalent to the identity that you define upon this gauging. So you have control about the spectrum of operators because you know what this identity is and where it comes from. So if we go back, as I said before already, I described beginning of today fully extended TFTs and non-fully extended TFTs and how to relate the two by saying that the identity that you have in the non-fully extended TFT is coming as a non-trivial element, algebraic element, in a fully extended TFT that you want to find. And if you do that, you end up having additional information about the theory you began with. Okay, so this is how the two things are related, this picture and the one that I just finished describing for the 4D n=2 case. So I think that for today, it's best to stop because I've already done a lot of things and I don't want to finish midway. So I think I will stop here for today and take any questions if there are. Thank you for your attention.